Mark McLean with Bridges and Tunnels, a drive through OpenStack networking.
Thank you. Yeah, so my name is Mark McLean. Just a little background on me. I am a member of the OpenStack Technical Committee. I was the project technical lead on Neutron for a few cycles, served on the core team for a couple of years now. Currently, I'm Chief Technical Officer for Aconda, Inc., which does network virtualization and routing. So when we start talking about Neutron, one of the things we want to take a look at is, why do we create Neutron? Sometimes I think having a little bit of motivation, especially when you're looking at OpenStack, and OpenStack originally had networking via Nova, is, one of the things is Nova doesn't necessarily support the creation of rich topologies. The technology choices are largely static. You get flat networking or VLANs in Nova. It's very hard to extend. And then lastly, how do we provide services, advanced service support, load balancing, firewall, VPN? So when we kind of take a look at those, like, why did we create, what are our motivations? We also have to kind of, what are the challenges when you're building out in the cloud? And so, you're taking a look at high-density multi-tenancy if you're running a public cloud. Interesting enough, even private enterprise is going to have very high density, especially if, say, you're building a very large-scale virtualized developer environment. You may have very high-density multi-tenancy, in which case VLANs may have troubles. VLANs are going to have trouble scaling. You get 4,000-ish of those. Depending on how your switches are configured, you probably get far less than default configuration. Additionally, on-demand provisioning, previously, if you needed to do networking, you had to have somebody go wire it and move wires around, and it was slow. As well as, need to build the ability to have workload mobility within the cloud. Maybe you need to upgrade hypervisors. Maybe you need to get off a node with a noisy neighbor. You need that ability, as well as have the ability to have IP mobility. For some workloads, that's important. For some applications, not so much. It really all depends on the design. So when we started taking a look at how we were going to tackle these challenges, you have network virtualization, which is kind of a catch-all for everything. You have overlay tunneling via VXLAN, GRE, or STT. We'll dive into those a little bit later. SDN, and now people have kind of started dropping the N, and you'll see like blogs and stuff that says SD and like X for the fill-in of software-defined networking functions. Via OpenFlow, which gives you the ability to program the switch flows. There's lots of different L2 fabric solutions. Always put question marks on here because as technology progresses, networking companies and vendors are always implementing new solutions. So we wanted to make sure we didn't box ourselves in. So taking all these components together, we kind of had to say, how do we distill these down? And really, what are the basics of really Neutron? So first thing we always took a look at is, what does the end user see? When you're using an OpenStack deployment, you see the compute API, the storage API, the network API, but ideally the user shouldn't have an idea of what's behind them. So in reality, the compute API could be backed by libvirt and KVM, the storage API could be backed by Ceph, the networking API could be backed by the modular layer 2 plugin. And then, so using that abstraction, in keeping it agnostic, the user's able to create just really a rich set of topologies. And so a little bit about terminology, because I know sometimes for those who don't always follow networking, typically what you'll find is, especially in Neutron logical constructs, you'll see the virtual L2 network is basically, the network in Neutron is just an L2 domain. It's a shared broadcast domain, traditionally like what you would find if you had all the hosts in a traditional data center on the same switch. Virtual subnet, so layer 3 construct we use for addressing and keeping track of the IPs. Virtual ports, because I know some discussions is virtual ports are basically, think of them as a port on a switch. And then when it comes time to wire a VM, is we connect the virtual port to the VIF by essentially plugging in a logical cable between them and wire them together. It's kind of the way you can think about the logical constructs. So, and very simple example here is you see kind of the breakdown of the responsibilities of, Neutron's responsible for the networks, the subnets, and the ports. Those are like three key entities for Neutron. And at the top, you'll see Nova is responsible largely for the VM, and ensuring the VIFs are created. Nice thing about that is using the API, we can create a really rich set of topologies where you can have routing, you can have NAT, you can create different tenant networks. If you notice that tenant A and tenant B have overlapping IP address ranges. With virtual networking, it enables you to build complete dev environments that replicate production environments. Also in high multi-tenancy, you don't have to worry about ensuring that the IP ranges are they don't overlap. It makes things easier as an operator as well. In a couple cases, you've noticed where we plugged in VMs into different L2 domains. So for our design goals, earlier kind of hit on it, is we wanted a unified API, whether you were using an open source implementation, whether you're using the proprietary implementation, that Neutron would function and act the same. We wanted to keep the core small, so the 3 basic logical entities you'll find in Neutron are network, subnets, and ports. That's the standard bare minimum Neutron. From there, we do add some more. You'll commonly find a couple others that I'll talk about. We wanted to make sure we had a pluggable open architecture. That way, as technology changes or as new projects are created, they can be integrated easily into Neutron, as well as to make it extensible. Again, new things are always coming out. People will develop new ways, easier management, easier ways to integrate, and we wanted to make sure that we could expose those to the user. So common features you'll find across all the plugins are support for overlapping IPs. Like I said earlier, 2 tenants can have the exact same IP range, and you won't have any issues. Traditional data center, if you have to do that, you end up having to write lots of fun switch configs to isolate bare metal. As well as configuration, we wanted to support DHCP and metadata. This is universally supported. Depending on some people will boot up their VMs using config drives. Some will want DHCP plus AWS compatible metadata service. We support both. And then the last thing is to support for floating IPs. Essentially, floating IPs allows you to have in v4, it allows you to have a static IP, so that way if you want to have a well-known IP, you can reserve it, and then you can assign it to VM instances. If you need to create or destroy a VM instance, the IP will stay. When we get to another common feature we support is security groups. They're very similar to AWS-style security groups. So you get support for overlapping IPs. This is a big significant difference from Nova, which doesn't necessarily support overlapping IPs and security groups. Another one of those is both ingress and egress rules. So ingress rules allow you to filter packets that are entering into the hypervisor, and egress rules allow you to filter packets that are exiting the hypervisor, as well as support for IPv6. IPv6 is a must. V4 space is running out. More and more providers are providing v6 connectivity. We wanted to make sure that Neutron was ready for it. I mean, IPv6 is at 20 years old at this point in time, so it needs to be there. As well as the ability to support VMs with multiple VIFs. Traditionally, it's not very exciting if you can only plug your VM to one network. Sometimes you need your VM to be plugged into multiple networks, depending on the logical topologies you've created. So architecture with Neutron and OpenStack in general, I think I'm required anytime you talk about an OpenStack, if you've seen this diagram, please don't run away in terror. It is quite scary. But what we're going to do is we're kind of really zoom in on a smaller part of it and take a look at what Neutron looks like. So we can take that scary diagram and really convert it down into something that's a lot simpler. Essentially, Neutron has several parts. It's backed by a relational database, which is where all the logical information. We have the Neutron server, which is an API service and an RPC service, which talks to the agents via a message queue. And so if you notice up there, I'll have L2 handles layer 2 in a lot of cases, layer 3 agents, DHCP agents. I also have multiple copies because one of the nice things for Neutron is you're going to likely have multiple copies either for HA purposes or just even for L2 agents in the hypervisors, you're going to have multiple hypervisors. So if we were to dive in a little bit more into the Neutron server, we have plugins, and so plugins generally come in 2 flavors. The way to think about a plugin, it's like a car. There's one engine to your car, that's your plugin that you get to choose from. the nice thing is you get to choose which kind of engine you have. You just can't have more than one. So if we start, we have one type of plugin called the Monolithic Plug-In. Basically what this is where the implementation implements the entire interface of the plugin from, ensuring how to, create, update, read, destroy of like networks, ports, subnets, as well as, in managing that. Some engines where monolithic plugins will say combine L2 and L3 together. The monolithic come in two types, which is proxy, where the plugin is a generic neutron logical call, and proxy again. Example of this would be if you were, in terms of OpenContrail is a proxy plugin. The calls come into Neutron. They do a little bit of glue, which rewrites the call more specific for OpenContrail, and then is applied on the back end. Or direct control, where some folks have taken the Neutron logical model and directly changed the state of the data path based on those calls and have implemented the entire logic inside their plugin. Optionally, we created another type of plugin, which is the modular. It's a full plugin, but we wanted to make it easier for implementers to integrate in with Neutron. So what we've done is we've really distilled down all to minimal differences between the L2 implementation and provided hooks. Commonly, what we were finding is a lot of recycled code between the plugins, and so we wanted to make it easier. There's two types of drivers in the L2. So when we talk about a mechanism driver basically handles the implementation. So if you're in the different of a type. So the types would be like VLAN, VXLAN, flat networking. And then the mechanism driver, if you were to have a network of, say, with a type of VXLAN, the mechanism driver would actually handle or it gets wired up and when the port comes up. For plugin extensions, they're just a way to add logical resources to the REST API. The server discovers them at startup. So as an operator, you have the opportunity to choose which extensions are installed. You also have the opportunity to selectively disable some. Some of the common extensions you'll find is, so the binding extension is how when Nova goes to create a VIF, it calls bind on Neutron, and that's what plugs in the VIF into the port. DHCP services, make sure that the DHCP server is set up. In most typical Neutron deployments based on open source code, the DHCP server is DNS mask. The layer 3 services. Provider networks are, deployments aren't islands. You need to connect them into your data center. You need to connect them into your core routing fabric. Provider networks provide that ability. Quotas, whether you're running public cloud, private cloud, or even small dev cluster, it's nice to have quotas, especially if you have automated service. Make sure they don't break. And then security group extension, it's a feature you'd find in Nova and AWS that we wanted to make that's commonly implemented. A couple other extensions which are very interesting that are implemented in most of the plugins are allowed addresses. Right now we prevent IP spoofing and MAC spoofing. So allowed addresses allows you to create rules that if you specifically know, hey, I have this VM that's, oh, by the way, going to be, might actually inject MAC addresses Neutron hasn't configured, you can, as an operator and admin, you can create rules to allow those to happen. Extra routes allows you to inject static routes either at the network level or at the host level, as well as extensions so that you can feed in the metering data into Ceilometer and then use that for billing or for other purposes. Start talking about the title of our talk, which was bridges and tunnels. The interesting thing is these pictures are taken in Budapest, and the chain bridge connects Buda and Pest, and immediately once you get off the tunnel, once you get off the bridge, it takes you into a tunnel right under Buda Castle. And so, oddly enough, there's also a roundabout. So if you think about a router, it allows you to sort all the cars as they go around the circle. It's kind of like real life networking with cars. Little dangerous taking photos, but So when we start talking about the L2 agent, kind of walking through the different components, the L2 agent runs on a hypervisor in the reference implementation. So if you're taking a look at what you would get in Neutron source code, it's going to communicate with the server via RPC. And basically all it sits there what it waits for is when it notifies Neutron, hey, a device has been added or removed to the logical switch on the hypervisor, whether a bridge or whether Open vSwitch. It doesn't really matter. They both work the same. And then once a new device is ready, it ensures the device is connected to the proper network segment, as well as applying the proper security rules. As far as L2 agents, the one other caveat is that there are open source implementations which do not have L2 agents. So if you're using a SDN controller, it may talk via some other protocol directly to the vSwitch on the host. As an operator, it really all depends on your technology. So this process may not exist depending on your technology selection. But if we're using the OVS agent, which is the open source one primarily that a lot of people will install with OpenStack, is Open vSwitch. It's Open vSwitch. It supports OpenFlow. Also supports another protocol called OVSDB for managing and configuring it. An OVS agent will provide tenant isolation for VLAN, GRE, and VXLAN. So typically you'll have so the flow would be you have the Neutron server, you have the OVS agent in green. The server would talk via RPC. The agent then in turn talks to the OVS instance on the local machine via OVSDB in most cases. Occasionally we do use OpenFlow. But for basic virtual, for lightweight virtual networking, you only have to speak with the OVS agent, OVSDB. If it was Linux Bridge, you would have like a Linux Bridge agent, which would just use standard kernel bridge utilities to manage. So when we talk about isolation and tunneling, we really have a couple different choices. So you have VLAN, which is 802.1q. It's, like I said, it's limited. You get 4,000-ish VLANs. Some of the switches, some of the hardware have different rules about which VLANs you can and cannot use. The underlay has to be aware of it so that if you're running with VLANs, you've got to make sure all your switches support it. You also have to, you also have to be prepared to have a larger layer 2 domain in many cases. Optionally, some folks will deploy GRE and VXLAN, which is basically encapsulating L2 in layer 3 or layer 4, depending on which protocol. It's routable, so the nice thing is this has overlay independence. So if we take a look at tunneling, one of the concerns and one of the challenges when we were building this is, typically if you have hypervisor hosts A, B, C, and D, and let's say we have an instance that gets spun up on A, and it needs to communicate with the instance spun up on D. If you don't know where to find that, you typically have to flood all the tunnels and create extra traffic within your deployment. One of the things the Neutron team worked on when we were implementing our tunnel is L2 pre-population. Benefit of that is we can actually add ARP responders to each of the hosts so that when A needs to talk to D, you only have to send the packet directly to D. You don't have to flood your entire network. You're not generating extra traffic. The layer 3 agents, so the basic one is basically starting with the router. It's typically, in a typical deployment, you'll run on a network node. You'll have some collection of network nodes. We use Linux network namespaces. It's a really cool feature that allows you to have, if you're not familiar with just using network namespaces that came out of some of the work for containerization, you basically get your own copy of the IP stack, which allows you to have overlapping IPs within the same host. Also, the L3 agent will run the metadata agent. So this is typically what you would see in many actual deployments. I've added an extra network node there because you're going to run multiple copies of them. So the agent, how it's implemented, like I said, it's implemented using network namespaces. So it's a collection of them. Each of them gives you an isolated stack. If you notice, we enable forwarding within those namespaces, both v4 and v6. Typically what this is going to provide is static routing. A lot of times people ask, when are we going to support dynamic routing? It's on our future roadmap. We haven't gotten there, so it's going to be static. You're not going to see any dynamic protocols like OSPF or BGP or any other related ones. It also runs the metadata proxy. So what you'll see is like namespace A and namespace B. They will have VS, which allow them to connect to the host namespace, which allows you to route to the rest of the network. Other layer 4 and above agents that we have load balancing as a service. It's essentially the agents, they'll run a network nodes, they'll run within their own isolated namespace. We use HA proxy for the open source implementation. It communicates via RPC. This is what interacts with other systems. Currently, right now, it supports layer 4. With the newest release of HA proxy, they're working on doing SSL termination, and the team's also working on adding layer 7 features so that you can do layer 7 load balancing. I expect to see most that works in the ELO. As well as one of the other services we provide is VPN as a service. Basically, it's based on OpenSwan or Strong Swan. It communicates over RPC. It's basically IPsec pre-shared key, so you don't have to deal with the authentication. It replicates what you find with Amazon's VPC in terms, VPC service in terms of basically being IPsec. Depending on how some of the other components within the OpenStack ecosystem evolve, there's work to include OpenSSL VPNs because people like those because they're very easy and trivial to configure. One of the issues with providing OpenSSL VPN is ensuring that you have the proper security around certificates and certificate management. There's a related project in OpenStack called Barbican, which is working on that and providing a secure store for those secrets, so that way, as a deployer, you can make sure that you have a very secure deployment. One of the questions that commonly comes up is what's in the latest release. So that area of the picture is actually Juneau, Georgia. It's in the middle of the mountains in Georgia. I'm actually from Atlanta, Georgia, just south of here. So it's kind of, even I had to go find it on a map since it's such a very, very small town. So one of the biggest features that we added is IPv6 in Juneau. So IPv6, a couple of the basics, it was important for us as a team to add it because the amount of traffic in IPv6, both in mobile, is significant, and also in terms of residential and business traffic is increasing, especially considering that the IP address space is essentially exhausted. What we support is we support RA supports. We use RA DVD. Damon to provide that. We provide a couple different algorithms for IPAM management. SLAC, which is the stateless auto address configuration protocol. Essentially what that does is it will take the MAC address, run a well-known algorithm on it, and generate an IP address for you, as well as sequential. A lot of deployers like the ability to say that my range in IPv6 is going to be, say, .1 through .250. Some like the ability to have, SLAC and have auto configuration. One of the issues and challenges with SLAC is that since it's based on the MAC address, if you ever change any bits of hardware in your server then gets a new address when it reboots. Now, virtually, it doesn't really matter as much because when you reboot the virtual instance, you're hardly ever changing out the hardware because, well, it's virtual. But there are some folks, if you're running bare metal, SLAC may not necessarily be the choice you always want. And then one of the things is that when you have RA and router advertisements, and if you're not familiar with V6, basically an RA router advertisement is the router sends out a message broadcasted out via IPv6 multicast that says, hey, I'm the router, here's my link local address. Downside of that is just like with rogue DHCP servers, if you don't secure RA announcements, you can have rogue routers on your V6 network. So we make sure in shared context and even in private context that your RA announcements are protected and that only the router authorized to send RA and that those messages actually do reach the hypervisor. So when I talked a little bit earlier about SLAC, again, we use RA for auto configuration. You're not running DHCP like you would normally traditionally find. The address is generated from the EUI64 address. One of the other modes we support is called what we entitled DHCP v6 stateless. Essentially, it's the same as SLAC. You still get auto-generated addresses, but one of the challenges with RA and SLAC is that you can't always send extra information. So in v4, we're used to DHCP. You can send extra options like additional routes. Maybe if you're doing TFTP or doing some other boot protocol where you need to upload an image, you can't send those easily, so we created DHCP v6 stateless. What that does is the RA announcement says, configure your address, but oh, by the way, make a DHCP request to get additional options. And lastly, we support more of a traditional DHCP v6 stateful. It's basically what you would find with v4 DHCP. The addresses and the leases are managed by the DHCP server. You can pass all the options that you traditionally find. All these are backed by DNS mask and RADVD. Another question that comes up constantly with v6 is, do I go dual stack, single stack? What we're really recommending for most folks is go dual stack, because your applications can support v4 and v6 unless you know that you have applications that are completely v6 ready. Both dual stack support is supported by the long-term, by both of the by all the current long-term support releases of the distros. So it works the best. You're less likely to find some warts and some challenges, because one of the biggest problems with v6 is that sometimes the underlying libraries won't always have the greatest v6 support, as well as. If you choose to go single stack v6, the metadata service, right now there's really not a standard in terms of config drive, and community has to we kind of have to, as a community, decide what that standard is going to look like. If you want to do metadata services at v6, what is the well-known address to request for? So typically, those who are doing large v6 only installments are using config drive to configure their servers and pass any needed metadata service, such as SSH keys. Another really big feature was distributed virtual routing. So if you remember before, I talked about where you had the core, you had the network node, the L3 service, runs on the node, it uses namespaces, everything we've seen before. But let's say we spin up a hypervisor, and this hypervisor is exceptionally noisy. Maybe it's DDoSing somebody. Or maybe it's answering lots of traffic, but over time it's going to saturate the link, it's going to build up, and it's going to saturate the entire core. If you have multiple network nodes, what you end up doing is have several choke points within your network. So one of the options available in Juneau is the ability for, have the ability for DVR, where basically what we do is do routing directly from the host. So we spawn up a little mini router on the host. It works again very similarly with namespace, but instead, if you have a floating IP assigned, we're able to route the traffic directly from the host into your core routing fabric. Benefit of this is that you're not saturating your links. Your traffic, in the case where you have a floating IP, is traversing the network directly versus having to go through a couple extra hops. So, people ask, deploy it, it's available in Juneau. We always joke that, you're going to deploy it, you're going to make sure the agent's uploaded on the hypervisor, you're going to associate a floating IP instance, and then lots of money, right? But not really. The big key win here is that all the north-south traffic is going directly from the hypervisor into your core routing. Now, for it is when you have east-west traffic. So before, very similar, but this time we have two hypervisors that are running on different nodes, or we have two instances running on different hypervisors. And if one wants to talk to the other, and let's say they're on different networks, the traffic has to go up through the network node, get routed to come back down. But if they both have floating IPs with east-west, you can actually do direct routing. Again, that's a win because you're removing logical hops. You're removing hops that each packet has to traverse to communicate. Now, if you're not using a floating IP on your instance, one of the things you'll find is essentially it's source NAT with masquerade. It's the same way OpenStack has worked for a while. And if you turn on the floating IP, then the source address is going to come from your floating IP address. A couple other improvements that we made is an improvement to security groups. We're now using IP sets. I don't know how many people are familiar with IP sets support in Linux. It's really awesome because you can aggregate, it's a lot easier to manage in terms of some of the IP tables rules. Also made the layer 3 agent HA. So in the network node, you can now run pairs of namespaces. We use contract D. We basically using VRP and syncing the two states up when one fails over in an active passive configuration via the namespace pairs. And then what we're currently working on in this iteration, 6 months, is kind of really paying down technical debt. One of the challenges of being a project that's 4 years old is when you're rapidly developing. Some calls that we made, 3 years ago, even some design decisions we made 2 years ago, when they looked great at the time, in hindsight, probably weren't the greatest. Also, some of our needs have changed over time. So one of the parts is recognizing those changes and paying down some of that debt to enable us to deliver even more services in the future. IPv6, we're working on prefix delegation, because one of the things as an operator is it's really hard when you have a big v6 address space. You don't want your tenants going, well, hey, this is my /24, sorry, not my /24, my /64, and manually having to create that. So we're working on v6 delegation, whether you're a private enterprise or public cloud or even smaller. The prefix delegation is kind of nice because you can, as an operator, you can configure a range, and then tenants can check out and request, and you have the opportunity for quotas to kind of say, okay, this tenant can have up to this many addresses. It kind of makes a very easier self-service model. Also taking a look at how we can improve the metadata service for v6. I mentioned IPAM. Traditionally, IPAM in Neutron has been tied to port allocation. What we want to do is provide external IP address management support. So that support you'll be able to integrate if you have a standalone system or you have an external system within your environment. You can actually write a little bit of glue code, and you can use that system to select and choose IP. Some of the larger enterprises who've had to work around this have really had to make like Franken Neutron installs, and it's kind of gross what they have to do. So we're trying to enable those, as well as facilitate dynamic routing. Most likely the first iteration of this is going to be creating a BGP speaker. So as you're delegating prefixes within your cloud, you need a way to tell your routing infrastructure how to find them. So the first iteration will probably be BGP. Some folks are pushing for OSPF, but that'll probably be a follow-on. And then the last is enabling a few of the NFV applications. NFV is one of those big buzzwords that you always hear a lot lately in telcos, but the interesting thing about NFV, when you take a look at the applications they're running, is there's really no difference than what a large enterprise would want. They still want reliable networking. They still want, uptime, good SLAs. So the nice thing about NFV work is, from our perspective of the team, it's actually good for the entire community. So lastly, just kind of summing it all up, is Neutron really is a unified API, has a very small core. Network subnet ports. Typically, you do find extensions to it with routing is very common. Pluggable open architecture. We have multiple vendor support. We have, I think, 23. I'm not sure if they're all up there now because we keep adding them in terms of, so as a deployer, you have lots of options. Some of them are open, some of them are closed. Some of the, even as yesterday, somebody announced a new open source open network controller based on OVS. So you're always getting more and more open options. Nice thing is it's both open in terms of code and also open in terms of development. So you have ultimate choice. And lastly is making sure it's extensible. A lot of times the open is in terms of more information. The Cloud Administrator Guide is on the OpenStack Docs website. It's really excellent, adds lots of options, and really talks in detail about a few deployment choices. And then if you're interested in just what the API is. So, any questions?
Yep. Do you have any facilities for ensuring IPv6 address stability other than floating IP?
So the question is how we ensure IPv6 address stability. Right now, we actually do not support floating IP with v6. One of the ways we're going to work on that is for address stability with the IPAM is you'll actually have the ability to allocate an address independent of a port. So if you want to, say, preserve an address that you manage outside of Neutron's normal port lifecycle, you would allocate the address to you, and then you can attach that address to any port. Because part of the reason we went that route versus floating IPs is typically floating IPs, you have a public address, which you then NAT onto a private. For us, we really want to push people towards doing public v6, at least initially.
So what do you then do about the issue where DHCP v6 by default is time and MAC based rather than just MAC based? So every time you reboot anything, you get a different DHCP address.
Anytime you reboot the instance. Yeah. So one of the ways we can do that is, so if you want to essentially a static IP, you could either switch to running static IPs. Config drive also gives you the ability as a operator to ensure that the configuration is written statically. Other alternatives that folks have using other config protocols. So basically, you get a Slack address and then have some other system which, some other config management hook which goes through and applies the static address. A lot of that work's still ongoing, mainly because the primary first driver of IPv6 and Neutron was Comcast, the large cable company in the States. It drove a lot of that work. So, any other questions? Good.
Hi. There was a bit of a sense in the last OpenStack Summit that this is going to be kind of a crazy year for Neutron. And there's certainly a lot of politicizing, I suppose, going on in the project as it is right now. You can see by the amount of vendors involved. I guess my question is, do you see a bit of a movement going on inside the Neutron community to attempt to oppose this politicization of the project by reinforcing the reference implementation to a point where it really stands to compete with a lot of the proprietary vendor plugins?
So, yeah, I mean, one of the challenges in terms of networking in general is network vendors have been competing against each other for, 40-something years, ever since there was the second one. So there is a little bit of political aspect. It's been that way in IETF. It's been that way in standards bodies, IEEE. Everybody wants their protocol to win. One of the things I do think we're relatively fortunate is there is a little bit of political, but for the most part, everybody participates together. As the core team, what we've been working on is splitting out the advanced services into independently managed projects. I would expect probably in the L or M cycle, we're going to look at taking the reference implementation and spinning it out into its own maintained project, because there is a community from operators, from distros, from other integrators who have invested. That's like L2 population came from one of the French telecoms, from in Orange. Into making sure the reference implementation did L2 population like you would find in a proprietary solution. So there is a growing and dedicated community to making that solution better. At the same time, what's been interesting is the rise of other alternative open implementations. So Open Daylight, Open Contrail, yesterday was OVN was announced, so seeing Ryu is a very valid OpenFlow agent. I mean, they each have their trade-offs, but it's kind of nice to see, because ideally in a perfect world, I'd like to see Neutron get to like what Nova is, where Nova is the generic wrapper on a hypervisor. You have KVM, you have Zen, you have, pick your back-end technology and let the merits in each of the ecosystems kind of work on their own. Without having to get dragged through, because there is a little bit of velocity drag of trying to maintain the public API and also implement a back-end system. And generally, or not generally, but it takes a huge generalist to work on both sides. So I'm kind of excited that I can split and make more focused teams.
Yeah, agreed. It's a bit of a challenge to try to, I suppose, get the benefits of Neutron spread back evenly, into the community, instead of having everybody trying to hold their grounds in each of the proprietary vendor plugins. So it's a bit of an opportunity to really kind of pool together. But I guess that's kind of shown itself with, as you said, the large free projects that have come out of it.
And large free projects. And the other thing is, there's a rise in large operators who want free solutions. They don't like paying. Commoditization of the controller market is really an inevitable thing. So you're going to see open source. You're going to see high quality open source implementations that the developers and deployers and integrators are pushing for. That's what you keep hearing at. It's like, I want free. I want free in all respects. They want high quality first class software. And so more folks I talk to, it's kind of nice to see and kind of refreshing. So, yep.
When talking about VXLAN, you were talking about that abstraction from the underlying switches, the fact that the switches don't necessarily have to support it. So the only question I have is, if you have VXLAN enabled with the layer 2 population and Open vSwitch, does that mean that your switches don't need to support at all that VXLAN function or even be aware of it? How does that work?
So in your underlay, when you're either running GRE or VXLAN, it's the same. Your underlay switching the nice thing about using overlays is you can make a very simple architecture within your data center. Typically, most folks will go more with a CLOS architecture. And your switches don't have to be aware that VXLAN is running because VXLAN is just it's UDP traffic. Now, what you are seeing, if you take a look at some of the merchant silicons and you take a look at, say, some of the Trident 2 chipsets, is you can actually terminate and do VXLAN in the top of rack switch. And so one of the cool, interesting features that we're also working on Kilo's hierarchical port binding. So what you can do is you can do VLAN within the rack to the top of rack switch, where you get hardware accelerated VXLAN NCAP and DCAP, which is a win in terms of throughput and performance, because most generic NIC cards can do VLAN pretty quickly. VXLAN not so much. The newer kernels do have native implementations of VXLAN, and OVS and traditional bridging do support that. But there's going to be a rise in solutions where you can do VXLAN top of rack, and so your switch is a little bit more aware of, and your switch at top of rack is the VTEP, the tunnel endpoint. And so there's several open source implementations that will be seen sometime in the next 6-12 months for that. Any other questions? All right. Thank you very much.
As a token of appreciation, we have a speaker's gift. It's all food.